Welcome to a new class on wireless communications. And in today's lecture, we are going to study different digital modulation schemes for wireless communications. And later on in the lecture, we would also study how would the performance be affected when it comes to a wireless channel. That is, what would be the performance of a digital modulation scheme under a wireless channel. So let's start with the topic. So the topic would be digital communication techniques for wireless communications. And the first thing that comes to our mind when we talk about digital communications is why we should go for a digital communications as opposed to analog communications that was used in the first generation wireless systems. So there are numerous advantages of digital communications as opposed to analog communications. For instance, you can achieve higher data rate with digital communications. You can encrypt your message in digital communications, which is not possible in analog communications. You can also have a channel code so that you can encode your signal before the transmission so that at the receiver end, if there are some errors induced by the channel, that those errors may be recovered using the channel coding. You can also compress your signal by using source coding. So these are different advantages. On top of that, the digital communication schemes are more power efficient as well compared to the analog counterparts. So here I have listed all some of the advantages of digital communications as opposed to analog communications. And then when we are talking about digital communications, so the digital communications is divided into different modulation schemes, and the broad classification would be linear versus non-linear modulation. So what would be different advantages of linear modulations compared to non-linear modulations? So the biggest advantage of uh, linear modulation is they have very good spectral efficiency. They have high spectral efficiency. That is the main advantage of linear modulation schemes. Non-linear modulation schemes such as FSK, GMSK are, on the other hand, are very power efficient and they are very robust to non-linearities of the channel. And for that reason, they were used in the second generation um, communication systems, wireless systems like GSM. But because of the desire for the data rate is growing day by day. So in 3G, 4G, and 5G networks, wireless systems, linear modulation schemes have been used like quadrature amplitude modulation, phase shift keying, etc. So now we'll talk about some of the basics of the digital communications, and we would start with the signal space concepts. So as you know, the main difference between digital communication and analog communication is that in digital communications you have finite number of signals from which you have to select what are you going to transmit. So you have finite number of symbols to choose from, and typically that number is represented by capital M. So you have capital M different unique signals that you want to transmit into the channel and detect at the receiver end. So if you represent your signal space S by this set, so this S is a set comprising of all possible signals that you would transmit in the channel, S1 of t all the way to Sm of t, then these are the M unique signals that you can transmit that into the channel. And then using the signal space concept, you map this infinite dimensional signal space to a finite dimensional vector space. So that is through the signal space concept, and that is very important, and that is what we are going to see here. Right? So the main goal of the signal space concept is that we would be able to represent these signals in the vector space, and that vector space would be of finite dimension. So let's start. Um, the signal space concepts. As mentioned just now, that we want, what we want is that we would represent our m different symbols that we want to transmit into the signal, into the vector space. So S is our set, S1 of t all the way to Sm of t is the symbols that you would want to transmit into the channel. In order to represent the signal space into the vector space, we make use of what are called the basis functions. These basis functions are typically represented by phi I of t, where this I typically varies from 1 to capital N. And remember, this N must be less than or equals to this M. So these are your basis functions. And in order to represent your signals, for example, Si of t is a signal you want to represent as a combination of the basis functions. You would represent Si of t as summation j equals 1 to capital N Sij phi j of t. So in this equation, this j is a variable varying from 1 to capital N. Remember, N, capital N, is the dimension, is the total number of basis functions you have. And this Sij is nothing but the projection of your signal Si of t onto the basis function phi j of t. So this Sij is nothing but integral 0 to capital T Si of t phi j of t dt. In other words, this is the projection of Si onto the jth basis function phi j of t, and this is nothing but the dot product of Si and phi j. Remember, these basis functions must have some properties, and one of the properties of these basis functions is that they should be orthonormal. These basis functions are orthonormal. These are orthonormal basis functions. And what do we mean by orthonormal basis function? Is that if you take one basis function, say phi I of t, another basis function phi j of t, you multiply and integrate these basis functions, then this product, this integral must be equals to 1 if I is equals to j, and this integral must be equals to 0 if I is not equals to j. That is what do we mean by orthonormality. That is, they are not only orthogonal to each other, that is, their dot product with each other is 0 if I is not equals to j, and if I is equals to j, their energy would be equals to 1. That means, and then they would be called orthonormal basis functions. So these basis functions um, can be used to represent all of your signals as 1 of t all the way to Sm of t. And if that is the case, that is, for example, this this equation we wrote here, if it is true for all I, right? So suppose let's define S tilde I of t to be equal to the same thing, summation j equals 1 to capital N Sij phi j of t, and if Si tilde of t is equals to Si of t for all I equals to 1 to m, then we say that our bases are complete. That means we have a complete basis for the set S, or in other words, these basis functions span the set S. Right? So under these conditions, we would say that we have complete basis. Or these basis function phi I of t, where I would vary from 1 to capital N, span the set S. So now this allows your infinite dimensional signal space to be represented into a finite dimensional vector space. And these vectors are also called constellation points. The signal constellation point of the set S, suppose we have the same set S, but now we are representing that set S in the vector form. That means that would have vector S1, that would have vector S2. How many vectors it would have? Capital M such vectors, because that is our the unique symbols that you want to transmit. And vector these these vectors are also called constellation points. So there is a procedure called Gram-Schmidt procedure through which you can generate n less than or equals to capital M basis functions for these constellation points. But the basis functions that are used a lot are are two basis functions. So suppose if capital N is equals to 2, so if we have two basis functions, then we can represent any signal Si of t as Si1 of t times phi 1 of t plus Si2 of t phi 2 of t, where remember these basis functions are typically the cosine functions and the sine functions. So where phi 1 of t is root 2 over t cosine of 2 pi fct, and phi 2 of t is nothing but root 2 over t sine of 2 pi fct. So if you have these two basis function, you can represent your your signal, infinite dimensional signals, by just a vector, which is only a two-dimensional vector, rather a complex number. That is why we also say that our baseband signal in the digital communication is a complex number. You can represent your baseband signal as a complex number because it has two bases on which you are going to by which you are representing your signal, and it would have one real part and one imaginary part. That means that imaginary part would be the projection on the orthogonal basis phi 2 of t. So suppose let's look at a constellation, specific constellation. We'll talk about these modulation schemes later as well, but for the sake of examples here, so suppose we have a 16 QAM modulation. By QAM, we mean that we have a quadrature amplitude modulation, and we have by 16, we mean you would have 16 points in the constellation. So let me draw a constellation of a 16 QAM. So you would have 16 different data points, which for which there uh, they would have different phases and they would have different amplitudes. So both amplitude and phase vary for the QAM modulation. So you would have these 16 points, for example, for a 16 QAM modulation, where this axis would be your phi 1 of t, and this axis would be phi 2 of t. And you can represent these different points. So these different points represent different signals. Right? This S is S1 all the way to SM. So this capital M is 16 in this case. This means you would have 16 unique signals that you need to transmit. And these are represented in the vector space here in this constellation diagram. And that would mean, to say this is S1, and say this is S2, for example. You can use what are called the vector calculus or the geometrical concepts in order to compute different important matrix here. So you can, for example, if this is a vector, so it would have projection both on phi 1 of t and phi 2 of t. This projection on phi 1 of t would be called Si S11 in this case, because I is equals to 1 here. And this projection on this axis would be called S12. And this S1 would be S11 times phi 1 of t plus S12 times phi 2 of t. And that is your transmitted signal S1. Remember, this distance from this origin or the length of this vector is proportional to the energy of the symbol. To be precise, L square is nothing but energy in the symbol S1. And then you can talk about, um, so this, you can see directly from the vector algebra that the energy Es would be nothing but S, or another energy in S1 would nothing but S11 squared plus S12 squared. And it can be proved that this would be nothing but integral from 0 to t S1 square of t dt. So this is the symbol energy. And then you can also make use of the distance between the constellation points to make different decisions. And we would be talking about that in detail. But for example, this distance between these 2 points, it would be called D12. That would be the distance between the constellation point um, S1 and the constellation point S2. And D12 would be nothing but mod of S1 minus S2. D12 squared would be S1 minus S2 squared. And if you have two vectors for which you want to compute the Euclidean distance, it is nothing but you subtract the different elements vector by element by element. You take the mod and you take the square and add. So, and if you take the under root, that would give you the distance. If you don't take the under root, that would give you the distance squared. So I'm stopping here and we would continue with this lecture in the next video.